Stationary waves in general, in principle, is always formed by two progressive waves moving in opposite direction. That in principle, stationary waves are produced when two progressive waves of the same type of equal frequency and speed overlap in opposite directions. Okay, so that is in principle how stationary waves are formed. You must have two progressive waves of the same type, same frequency, same speed, overlapping when they're moving in opposite directions. That is in principle how it's formed, but not always do they. That is in theory, okay. But in practice, they don't always form. Okay, stationary waves in practice only form under certain frequencies. Okay, and they are demonstrated by a few different apparatus. The first one that you will learn is formation of stationary waves using a stretched string. Okay, so basically what you have here is a string. Okay, what you have here is a string that is connected to a vibrator. The vibrator in turn is connected to a frequency generator. The frequency generator causes the vibrator to vibrate according to a certain frequency. So maybe you can set your frequency generator to vibrate at 100 Hertz. This will cause the vibrator to vibrate at 100 Hertz. You can also change it to vibrate at 500 Hertz. The vibrator will vibrate at 500 Hertz. So when you set the frequency here and cause your vibrator to vibrate at that certain frequency, as this vibrator moves up and down, it will cause a wave to be formed. Okay, what you have is that as your vibrator moves up and down, you will cause a wave to be formed that moves towards the right. Okay, but when you look at further down the string, there's something like a physical obstacle. You have something called a movable bridge here that's preventing the wave on the string from moving past it. So what happens is that when this wave, the blue color wave that I showed you here, hits the movable bridge, it will get reflected back. Okay, it gets reflected back in the opposite direction. Okay, it gets reflected back in the opposite direction. Now, in principle, since you have two progressive waves of the same speed, same frequency, traveling in opposite directions, overlapping, by right, you ought to get a stationary wave. But the fact is that they don't always occur, all right? It only occurs at certain set frequencies, okay? So that is the key take-off point here. Just know that when it comes to practical examples of stationary waves, they don't always form at all frequencies. They only form at certain frequencies. So what frequency is it forming is what you are interested in knowing right now. Okay. Yeah, another thing I forgot to mention is that this string here is resting on a movable bridge, but at the same time, the string is actually being passed over a pulley with a weight at the end. This weight here is actually providing tension to the string. Okay. So now, what we'll tell you now is that at those certain frequencies where stationary waves are formed, the first time you see a stationary wave being formed, it will look like this. Okay. The second time you see a stationary wave being formed, it will look like this. The third time you see a stationary wave being formed, it will look like this. Sorry, I needed to add the loops. It will look like this. Okay. So the stationary waves will be formed at certain frequencies. So at those certain frequencies, you start to see some difference in the loops in the stationary waves. The first time you see being formed looks like this, one loop only. The second time you see a stationary wave being formed, you see two loops. The third time you see three loops. So from here, you can recognize a pattern. The fourth time that you see a stationary wave being formed, you will have four loops. The fifth time will be five loops. Okay. In all those cases where you have formation of stationary waves, notice that there's one thing that is always common. This part here would always be node. Okay, so just now I mentioned briefly to you in the previous question that any physical barrier will always have a node. once you form a stationary waves. Okay, so over here you can see that both ends of the string are always assumed as nodes. Okay, so say this one is the first formation of stationary wave, second formation, and then the third formation, so on and so forth. So to give you an idea of what I actually mean by that, I'll just play you a video of stationary waves on the stretch string. Just give me a few seconds to find out where is that experiment. Okay, I found it. I'm going to share the video with you now. Okay, let me just disable the sound. Okay, so you should be able to see on your screen right now some sort of video that's paused. So what you're seeing now is the signal generator. Okay, this one controls the frequency. It's connected to a vibrator that you're seeing right now. Okay, this one here is your vibrator. Okay, and then after that, you notice that it's connected to something else. This one is your string. Okay, before this, going all the way to here, like this one here, there was a signal generator here just now. Okay, there was a signal generator here just now that you saw. Okay, so what you're doing now is that you're switching on the signal generator, causing the vibrator to vibrate at a certain frequency. So in turn, it causes the string to move up and down. Okay, so this one here is the first formation of stationary wave. Okay, they're showing it again. Signal generator, set the signal generator at a certain frequency. Okay, so this one is the formation of your stationary wave. You notice that this one is, you can clearly see that there's a loop, right? There's a loop that it forms like this. At that frequency that where you form a stationary wave, you can clearly see a loop. Now, what you're seeing now is another different frequency where your stationary wave is formed. You can see that you're going to form two loops here. Okay, let me just back out the video a little. See these two loops, and then the next frequency, you're suddenly going to get three loops. I post out the video for you. You're going to see three loops. 1, 2, 3. Okay, so this one is the effect of you increasing the frequency of a signal generator to give you those stationary waves. All right, so the more you increase the frequency, the stationary wave that is formed subsequently will have more loops. Okay, but bear in mind that the frequency at which these stationary waves only occur at certain frequencies. They don't occur at all frequencies. If let's say you have a frequency that is different, that's not the certain frequencies that I mentioned, you don't see these loops here. Okay. Okay, now this is another one. This one is giving you 4 different loops. It's very faint. You see, this is one loop here. Okay, this one you have 4 loops, I think. But I drew 5 out. But you get the idea. The loop is getting more and more. Okay, you are getting 4 loops here. All right. So then they increase more, you're getting even more loops again. So you see, as they increase, the frequency is quite specific. Okay, so I'll just play the video again so that you can see it again. All right, so I'm just gonna show it again to you. I'm just gonna erase everything. So just look at it carefully. Look at the formation of the stationary wave at certain frequencies only. First stationary wave, second stationary wave, third stationary wave, then fourth stationary wave, and lastly the 5th stationary wave. Okay, or they even went to the 6th stationary wave. So notice that the loops are actually getting more and more, but the amplitude seems to be the loop tends to be getting smaller and smaller Okay, so this one is formation of stretch string on formation of stationary waves on a stretch string. Okay, this is what I meant. Okay, now you're interested in finding out what are the frequencies in which your stretch string is forming a stationary wave. That one, I need you to look at page 22. Okay, so if I give you the example of the stretch string and we ask you to determine the frequencies at which the stationary waves occur. So for the case of the stretch string, it looks like this. Okay, both ends are fixed, both ends are physical barrier. So the stationary waves that could be formed is something that looks like this, right? Notice that both ends are always going to be a node. So if I have more stationary waves, all I'm doing is I'm adding more loops to the wave. Okay. So now let's do the analysis here. If I tell you the first stationary wave is being formed at frequency f0, what will be the other frequencies in which I get the second and third stationary wave? So now based on what we have here, say for example, my given length is L, stretching across this end to this end. Okay. Now this one, I know for a fact it is a node. This one I also know for a fact is a node. Distance between adjacent nodes is going to be lambda over 2. In your case, is equals to L. So now you see lambda is equals to 2L and is at frequency f0. Okay, so this is the first information that you have. If say you try to increase your frequency until the point you get the next stationary wave, this is what you're supposed to get. You look at the diagram below here, this is what you're supposed to get. You're still having a node here. Your total length is still L. But now how many wavelengths do you have here? In terms of wavelength, how would you look at this? This one you understood is, sorry, I shouldn't be using red, same color. This one you understood it as being half a wavelength. This one is also half a wavelength, right? Because you know that distance between adjacent nodes will always be equals to half a wavelength. Right now you have two half wavelengths equals to L. So you try to rearrange this, eventually you get that lambda is equals to 2L divided by 2. Okay, now you want to compare between this one and this one. Now from here to here, notice that the first one is 2L, the second one is 2L over 2. Your wavelength has actually decreased by 2 times. Okay, wavelength has actually decreased by 2 times. So if your wavelength decreased by 2 times, it should mean that your frequency must increase by 2 times. Because remember, under the wave section, I mentioned before that frequency is always inversely proportional to your wavelength. Okay, so because it came from this, V is equals to F lambda, V is constant, F would thus be inversely proportional to your wavelength. And the other one that I always tell you was frequency is inversely proportional to T because frequency is 1 over T. But we're not using this one right now. We're using this one. Okay. So this one, you see that for the formation of your second stationary wave, your frequency must be twice of the original one. So this one must be at 2F0. Okay. Now we repeat the analysis again for the third one. If I go and increase the frequency again until I have another stationary wave being formed, this time I will have 3 loops. So this one will be node, this one will be node. So everything here will also be a node. Okay. So from here, I notice that I'm having 3 half wavelengths. Okay. 3 half wavelengths is equals to L. So I again try to make lambda the subject here. Lambda is 2L divided by 3. Okay, so you compare with the first time you have a stationary wave. From here to here, wavelength decrease 3 times because 2L divided by 3. So subsequently, your frequency must be increased by 3 times. So the third time you're going to have a stationary wave will be 3F0. Okay, so from here, you can actually see a pattern already. The frequencies in which you will have a stationary wave being formed will be F0, 2F0, 3F0, 4F0. So the next few ones would probably be 5F0, 6F0, and so on and so forth. Okay, so if I tell you that your first time you have your stationary wave is at 100 Hertz, this one will be 200 Hertz, this one will be 300 Hertz. Okay, this is formation of stationary waves using stretch string. Okay, this is what you have. Okay, now there are also some other examples of formation of stationary waves using different wave types. The first one that you see here is for stretch string, but a common one that you often see is formation of stationary waves for sound waves. Okay, so what we'll tell you here is this. Normally what you do is that you take a glass tube or measuring cylinder. Okay, in your case, you have a measuring glass tube that is closed at one end here, and then you mount it out horizontally. Now, what you do here then is that you will spread some sort of fine powder or dust along the length of the tube. Okay, which is what you're seeing here. All right. Then after that, what you do is that you place a loudspeaker at the open end of your tube. Okay, your loudspeaker is connected to a signal generator, which is used to drive the loudspeaker, as well as varying its frequency. So in principle, if your loudspeaker is on right now, it's going to cause a sound wave to go to this direction. It hits a glass tube, it will get reflected. Okay, it will go the other way. So in principle, two progressive waves, opposite direction, same speed, same frequency, overlapping should give you stationary wave. But again, as I mentioned to you, in practice, it doesn't happen at all frequencies. It only happens at certain frequencies. That certain frequency is what we are interested in finding out. Okay, so for example, right now, if we so-called have that certain frequency where stationary wave is formed, what you will tend to see is that fine powder that we initially spread along the length of the tube, it will start to shift into these little bumps that you see here. You see those stationary waves start to shift into bumps like this. Initially, they were finely spread, okay? They were evenly spread along the length of the tube. But once you have formation of a stationary wave, you see that the fine powder tends to be shifted, okay? One easy way of looking at it is, you can just think of it as this. Sorry, I'm trying to draw it properly. So please excuse the drawing. What you have is something that looks like this. Okay, this is a horrible drawing. Okay. Okay, something that looks like this. You have a stationary wave that kind of looks like this. Okay, you have formation of stationary waves, all right, inside the tube. Okay, so your fine powder will be shifted once you have a stationary wave being formed. Okay, so what we'll tell you here now is that when you see the fine powder accumulating, those are actually your nodes. But when you see the fine powder spread out almost all the way to the bottom of the tube, those are your antinodes. Okay, so the reasoning for that will be that we will tell you that at the antinodes, the molecules there are vibrating with the largest amplitude. They are actually shifting the powders away from that position. But then at the position of your nodes, you know that the particles don't vibrate. So whatever particles that is being shifted by the antinodes, it will just accumulate at the node. The air molecules at the nodes themselves are actually not vibrating. Okay, because you already know the definition of nodes, they don't vibrate. But then for antinodes, you also know the definition that molecules will vibrate with maximum amplitude. So what's happening now is that the air molecules vibrate with maximum amplitude. They're pushing the fine powder away. Okay, pushing them onto your nodes. That's why you see these things here, the little bumps here. Okay, we call it, as you can see, that the fine powders are actually forming equally spaced peaks. Okay, this is one observation when you have formation of stationary waves for sound. Okay, another observation that can also be seen when you have formation of stationary waves for sound is when you suddenly hear a loud sound. Okay, when you try to form a stationary wave using a loudspeaker, initially your loudspeaker will just be buzzing in a monotonous tone, but once you have a stationary wave being formed, you will notice that the sound suddenly becomes really, really loud. That is where you have stationary wave. Okay, so just bear this in mind. Whenever you have formation of stationary sound waves, you will see either these two observations. Okay, so again, stationary waves in your case are only formed at certain frequencies. At any other frequencies, you don't see any of this thing happening. Okay. Yeah, and another thing I should probably mention to you is that because this is sound waves, okay, because this one is sound waves, just now I mentioned to you sound waves are longitudinal wave. Okay. So since they're longitudinal wave, the oscillation of your particles will always be parallel to your wave direction. So if I look at the tube right now, the oscillation of my particles, air molecules, as sound travels through it, it will not be up and down, okay? That is wrong. It will actually be left and right, parallel to the direction of wave travel. What I mean is that it looks like this. You oscillate left and right, left and right, left and right, left and right, like this. So oscillation is parallel to wave direction. Okay, so just now I mentioned to you the antinodes is where the amplitude of vibration is maximum, right? So your air molecules is moving left and right with the maximum possible amplitude. In the process, it's shifting your powder away. It shifts it to your node when there's no vibration. Okay, so that one is okay. All right, now another thing I should probably mention to you is that when it comes to the formation of stationary sound waves, you don't necessarily always use a closed tube. Okay, you could be using an open tube also. The same thing could also occur. All right, where what will tell you is that you could put a loudspeaker here. Your loudspeaker will produce sound waves, and then it travels through the length of the tube. But then once it hits the other end of the tube, it will actually get reflected back. Okay, it will actually get reflected back. The reasoning is probably because, you see, all your air inside your tube is being squashed together. Your density of air inside the tube is different than the density of air outside. Okay, there's a difference in density between inside the tube and outside the tube. So when sound wave travels from left to right here, because it encounters the difference in density, it's kind of like something like an invisible wall. So the sound wave will actually, rather than travel outside, a part of it will get reflected back. Okay, so in principle, again, two waves, opposite direction, same speed, same frequency, overlapping, you're going to get stationary waves again, right? So just bear in mind that the open tube here can also give you a stationary wave. Because of the difference in density inside and outside the tube, your sound wave will actually get reflected back, giving you stationary waves, okay? Right? Now, an important thing for you to know here is this. If both ends are open, there will always be an empty node at both ends. Okay? Empty node, empty node. If the tube is closed at one end, then the node will be at the closed end and the empty node will be at the open end. Okay? So just bear this in mind. Okay. So in summary, just think of it as this. An open end will always result in an empty node. A closed end or fixed end or physical barrier would always result in a node when it comes to the formation of stationary waves. These two statements is actually under page 23 of your notes. Okay, so just bear that in mind. All right. Okay, so now that you know that stationary sound waves can be formed using tubes, again, we want to know what are the frequencies in which you form those sound waves, stationary sound waves. So you do an analysis similar to what we've done for the stretch string. So let's just say right now, again, you refer to page 22. Say right now we want to analyze the formation of stationary sound waves for an open tube. Both ends are open. Okay. So this will give you the appearance of those stationary sound waves. Because both ends are open, you will notice that this will always be empty node. Okay. Now, when it comes to trying to predict the shape of the waves, there's this easy way that you can do. What you want to do is you try to draw a general form of your sound wave, of your stationary wave that often looks like this. Okay. Then after that, you always look at the end condition. If I know that this is empty node and empty node because both ends are always closed, what you do is that, okay, based on this general form of stationary wave, the smallest stationary wave I can get where both are empty nodes will be this one. This one will be my first one. So if I want to get another bigger stationary wave, it must still be node to node. Sorry, it must still be empty node to empty node. So the next possible shape could be this one. This one will be my second. Then I know that for the third stationary wave, it must also still be empty node and empty node. So the next possible shape would be this one. Okay, that's how I get this shape. It was not randomly drawn. It's following a certain logic there, based on the conditions of the stationary wave, based on the end conditions for the stationary wave. Okay. I mean, you can also do the same analysis for the stretch string just now, because I know that both ends are fixed. It will always be node as well as node. So for that case, I always I again can draw the general pattern of a stationary wave and then see the shapes from there. So let me just go to the right hand side here. If I know that it's always going to be node and node, node and node, this one could be my first one. So the next stationary wave I get must also be a node. So this one will be my second one. Then after that, if I want to get the third one, okay, it must again be node and node. Okay, it must again be node and node. So this one will be my third one. Okay, so this is how you predict the shape. You must first know what are the end conditions. If it's node and node, you can predict it like the way I just did. If it's antinode and antinode, you can predict it like the ones that I've shown on the right diagram here, on the left-hand side of this diagram here. Okay, so that's how I get these shapes here. All right. Okay, now from here, I want to do an analysis. The first formation of my stationary wave occurs at frequency f0. Okay, the total length is still L. So now from here, this one is antinode and antinode. Okay, distance between adjacent antinode will be equals to half wavelength. So now I get L is equals to lambda over 2. So lambda is 2L equals to F naught. Okay. Then the third one, the second stationary wave, I get this shape here. I can see that this one here and here is lambda over 2. This one here again is lambda over 2. So I have 2 lambda over 2 because these are distance between adjacent nodes and adjacent antinodes, and this is also a distance between adjacent antinodes. So I have 2 lambda 2, 2 half wavelengths equivalent to L. So I rearrange this, I will get lambda is equal to 2L over 2. Okay. Now if I compare with the first value I had, lambda has decreased by 2 times. Therefore, frequency must increase by 2 times. So this one will occur at 2 F naught. Okay. Then after that, I can repeat the analysis for the next for the next stationary wave. This one again is lambda over 2. This one again is lambda over 2. And this one again is lambda over 2. I have 1, 2, 3. So I have 3 lambda over 2 equals to L. So from here, lambda has decreased by 3 times. Frequency must increase by 3 times. So my next occurrence of stationary wave will occur at 3 times the frequency. So this one will be F naught, 2 F naught, 3 F naught, 4 F naught, and then subsequently 5 F naught, 6 F naught, 7 F naught, and so on and so forth. Okay, so this is how I will produce those stationary waves. All right, okay, then I'll just clear off this diagram here. Okay, then after that, the next one, the last one will be if you have a closed tube, one end open, one end closed. So in this case here, again, just look at the end condition. For the open end one, this one I'll just skip a lot later. This one is open end. This one will always be empty node. And then for the closed end, this one will always be a node. Okay, so to predict the shape, just always do the method that I just described. Draw a general shape of your stationary wave. Look from there, what are the possible shapes for antinode and node? Okay, so in my case, I have antinode and node. This is the first possible one. The second one will be antinode and node again. So this one is the second possible one. So the third one will also be antinode and node. This one will be the third possible one. Okay, that is how I produce these shapes here. Okay, so you do the same analysis as before. Now this time, this one is node, sorry, antinode and node. This one is going to be, sorry, I shouldn't use red. Why do I always use red? Okay. Okay, this one will be quarter lambda. Okay, now just now we already did some question that talks about that. Distance between adjacent node and antinode will always be quarter lambda. So in your case, L is quarter lambda. Lambda is 4L. It occurs at frequency of F naught. So when I go to the next shape, I can see that this one here is quarter lambda. This one is quarter lambda. And this one is quarter lambda. Okay. I have 3 quarter lambdas equals to L. So lambda is 4L divided by 3. Okay. So here you will see that lambda decreased 3 times. Frequency must increase by 3 times. So this one occurs at 3F naught. Okay. Then if I do the same analysis again for the next shape, you will get this kind of thing. So this one is lambda over 4, lambda over 4, lambda over 4, lambda over 4, and lambda over 4 here. So 1, 2, 3, 4, 5. You would have 5 quarter lambdas equals to L. So lambda is 4L over 5. Compared with the first value, lambda decreased by 5 times. Frequency will increase by 5 times. Okay. So this one will occur at 5 F naught. Okay, this will occur at 5 F naught. Okay, so from here you can then try to predict already what are the possible frequencies where you're going to have stationary wave. You're going to have F naught, 3 F naught, 5 F naught, 7 F naught, 9 F naught, and so on and so forth. Okay, so this is how you do this for your open tube. Okay, right. Now, just look back at your question in your worksheet. Page 20. There's an example on this actually. Page 20. Okay. Look at page 20 of your worksheet. Okay, page 20 of your worksheet, we actually just did question 24 just now. Okay, under page 20 of your worksheet. I want you to look at question 25, the question next to it. Okay, right, this is that question there. Now you have a musical instrument called a bugle. The musical instrument called a bugle that is a long tube with a mouthpiece at one end. The other end is open and flat. A musician maintains stationary sound waves with a note at the mouthpiece and an anti-note at the other end. The lowest frequency of sound that the bugle can produce is 92 Hz. Which different frequencies of sound can be produced by the bugle? Okay, so basically here they're asking you what are the different frequencies in which you're going to produce a stationary sound wave. Okay, they already told you the lowest one that can be used to produce that one, the stationary sound wave, is 92 Hz. This is kind of like your F naught. Okay, so they want the subsequent frequencies in which you can have the stationary sound waves. Okay, so notice that they already kind of mentioned to you what are the conditions. They told you that at the mouthpiece, which is this one, you will have a note. So this one will always be a note. But then at the open end, at the other end, which is open, it will be an anti-note. This one will be an anti-note. Okay, so when you want to do the analysis for this, to look at the different frequencies and then find out what are the, to look at the different frequencies in which you get the stationary sound wave, you will do an analysis similar to what you just saw in the notes. This one, under page 23, the example that we just did. Okay, notice that the example for the question, they say one part is note, one part is anti-note. Isn't it the same as the example in question 23? Sorry, yeah, isn't that the same as the example in page 23, not question 23, page 23 of your notes? So when you do the same analysis, you notice that your frequencies in which you're going to have the stationary sound wave is this, is odd number of your F naught, 1, 3, 5, 7, 9, 11, 13. Okay, so what you do is that you just do the analysis. You will know that your frequencies must be F naught, 3 F naught, 5 F naught, 7 F naught, and so on. So if F naught is 92, 3 times of F naught will be 276. 5 times of F naught would be 460. 7 times of F naught will be 644. So from here, you can see that your only possible answer is C. 92, 276, 460, 644, and 828. Okay, that's how you would do a question like this. Okay, this one is for this. All right. Okay, this is the simplest example of that. Okay, then there was one last part that I needed to kind of explain to you. Okay, so now you get the idea how to do this. All right. There's one last part that I also need to do for you. Okay, this one is on the page 24. Okay. Now, notice that for page 22 and 23, covering the examples just now, notice that there was one thing here. Notice that in your case, for all those examples, the length L is actually fixed. When I have the different stationary waves produced from the first to second and third, the length L never change. It's only the wavelength and the frequency that change when I produce those stationary waves. It applies to the first example, it applies to the second example, as well as the third example. In all those examples, when I had the different stationary waves produced, my length never changed. Only the frequency was being changed to produce the stationary waves. Okay, so keep this in mind. That's why I wrote it here. For your previous examples, length L is maintained constant while frequency F is varied to produce stationary waves. You increasing the frequency will increase the number of loops in the stationary waves. Okay, bear in mind that there will also be cases where rather than changing the frequencies like you did just now, you instead vary the length to produce your stationary wave. Okay, so this is another separate example that you will often see in your questions. They don't change the frequency, they change the length instead. So over here, what we'll tell you is that increasing the length instead will now increase the number of loops in your stationary wave. Okay, so look at the last page of your notes. This is the example of that. Now, changing length of tube L to produce different stationary waves. Okay, say for example, right now you have a closed tube like what you see here. All right, what we'll tell you now is that when you have your stationary waves, you're gonna get these shapes. Okay, notice that the end condition is still the same. Open end will always be anti-node. Closed end would always be node. Okay, the shape that you draw will be based on that. Okay, so the further you go, the more stationary waves you produce, you're gonna get more of these loops. All right. Okay, so one thing that you can do now here is that you see the length is being varied. The frequency never change. If I told you that this one is produced at frequency F0, this will also be produced at frequency F0. This will also be produced at frequency F0. Okay, this one I did not change the frequency. I maintain it the same. But the only thing I changed was the length. Okay, so how do I get the different lengths that will give me my stationary waves? All right, so this time you're trying to get the different lengths that will give you a stationary wave, not the different frequencies. The previous one was talking about the different frequencies. Now you're talking about the different lengths. Okay, so the easy way to look at this would be to do an analysis similar to what I've just done for you. This and this would be quarter wavelength. Okay, so I can say that length L1 is actually equals to lambda over 4. Okay, then after that I go to the next one, to the next stationary wave. This one you will notice that this one is quarter lambda, this one is quarter lambda, and then this one is quarter lambda. For pre-quarter lambda, you're having L2. Okay, But notice that now, in your case, lambda over 4 is actually L1. So this one is actually equals to L1. Therefore, L2 will be 3 times of L1. Okay. If this one was your stationary wave was occurring at length L1, your next stationary wave is occurring at 3 times the original length. Okay. Then you repeat the same analysis again for the last wave, which you have here like this. So I'm just going to shorten some of those stuff out. So basically all of this is going to be quarter lambda. All right. So 1, 2, 3, 4, 5. You have 5 quarter lambda. Okay, L3 is 5 times quarter lambda. But again, quarter lambda, as you can see here, is actually equals to L1. So you're going to get your new stationary wave at 5 times the original length. Okay. So that is how you would do this. If you're trying to change the length in order to get a stationary wave. So important thing, I just need to reiterate again, frequency is not changed. Okay. So F remains constant. And also another thing I should mention to you here is that the wavelength remains constant too, because frequency did not change. Okay, this lambda here is the same as this lambda here is the same as this lambda here. They're basically the same. All right, because you did not change the frequency, you did not change the wavelength too. All right, you're only changing the length. Okay, for the previous one, you changed the frequency and you were changing the wavelength actually. Okay, yeah, maybe I should make a mention here. For the previous frequencies that you have here, for the previous examples that you have here, I should mention this to you. Your frequencies here are not the same. Likewise, your wavelength here are not the same. Although I make use the same symbol here, they're not the same. This one, if you really want to be really detailed, this one is lambda 1. This one is lambda 2. This one is lambda 3. Okay. Your frequency here was actually being changed. Your wavelength is actually changing. And there are different values. Okay. So don't mistake this one as being constant wavelength. Right? The wavelength is actually being changed. In general, as long as you did not change the frequency, you won't be changing the lambda. But the moment you change the frequency, you will change the lambda. Okay, so that's just one thing I should mention to you. Okay, let me just find an example to show you what I mean by that. Give me a second also. 11. Okay, we go to page 11, question 28, just to illustrate to you the questions. Page 11, question 28. All right. Okay, just look at page 11, question 28. The diagram shows you a tuning fork above a tube of air of length 25 centimeter. A stationary wave is set up in the tube with the same frequency as the tuning fork. The lower end of the tube is sealed. The minimum length of the tube with the lower end sealed creates a stationary wave. What will be the other lengths of the tube sealed at the lower end that will create a stationary wave? Okay, so what will be the other lengths that will create for you your stationary wave? Okay, this one is again a tube with sound wave being used to produce a stationary wave, but this one is mounted vertically. The example inside your notes is mounted horizontally. It's actually the same thing. Don't bother about the orientation. It means the same thing. Okay, so of interest to you was that you saw that this one is a closed end, right? This one will always be a node. And then this one at the open end here, this one will always be an empty node. Okay. So another thing that you should see here is that they mentioned that the stationary sound waves setup has the same frequency as the tuning fork. Meaning to say, if your tuning fork had a frequency of f0, when you have your stationary sound wave being formed, it will also have that same frequency. Okay, so now I'm interested to know what is the first form of the stationary waveform. The first form of the stationary waveform would look like this. Okay. The first form of the stationary waveform will look like this. Okay, this is the simplest one. Okay, the second and third one would basically look like what you've seen in the notes. Just tilt it vertically, you tilt it to the vertical orientation and you'll be able to see it. Okay, so first one like this, second one like this, third one like this. You do the same analysis as before, you will notice that the lengths for your stationary waves would be L1, 3L1, 5L1, and 7L1. Okay, so if let's just say I try to do for your case right now in your question, this one will be your L1. This one will be your L1. So the other instances that will create for you your stationary wave will be L1, 3L1, 5L1, 7L1. So L1 is 25, 3L1 is 75, 5L1 is 125. Okay. And then 7 or 25 will give you 175 centimeter. So look at what are the possible ones. You can see very clearly that it's going to be answer D. Okay, 75, 125. Okay, so this one is one way in which you would do this question. Okay, this is the by far the easiest way I know to do this kind of questions. That you have no choice but to somehow draw the a simple sketch of the diagram and then analyze from there. Okay, so this one is for this. Okay, so the answer is D. Okay, then I go through another one for you. Okay, let me just try and find another suitable one just to illustrate to you those different examples. Is it 29? Ah, okay. Maybe we go to page 29. Let me just write it out for you on the board. Have a look at page 29, question 24. Okay. All right. Okay, so yeah, this one again is another similar example where you are just changing the length, but you did not change the frequency. Okay. So with that in mind, let's just read the question. They tell you right now, the diagram shows an experiment to produce stationary wave in an air column. A tuning fork is placed above the column. It vibrates and produces a sound wave. The length of the air column can be varied by altering the volume of water in the tank. Okay, here your length of your air column is this one. This is your length of your air column. You can alter it by changing the volume of water in the tank. Basically, what you would do is that you have a tap here. If you open this tap, water will flow out, and then the water level here will drop. So when your water level drops, your air column becomes longer and longer and longer and longer. Okay, so that's how they vary the volume, the length of your air column. Okay, so just bear that in mind. Okay, now the next part of the question mentioned this. the tube is filled and then water is allowed to run out of it. Initially, they fill it out with full with water and then they let water run out. Okay, as water is running out, they notice that you have two stationary waves formed. The first two stationary waves occur when the air column lengths are at 0.14 and 0.42 meter. What is the wavelength of the sound wave? Okay, so this one, you can just think of it as this. When you have the first formation of your stationary sound wave, okay, now this one, you can clearly see that this one is a closed end, right? This one will be a node. The top part is an open end. This one will clearly be an antinode. Okay, so the most basic shape of a stationary wave that can be formed is this. Okay, this one is at 0.14 meter. Okay, now when you have the formation of your second stationary wave, your air column is longer now. Okay, the air column is now longer. Column is now longer, right? So I'm trying to draw it to scale for you. The second formation of your stationary wave would be like this. Would not look like this. Okay. This one is 0.42 meter. Okay, so this one was the second stationary waveform. Okay, now they want you to find out the wavelength of the sound wave. Okay, they want the wavelength of the sound wave. Notice that this question is different from the others just now. They don't want you to find out what are the different lengths. They want you to find out what is the wavelength of the sound wave here instead. Okay, so here I think I mentioned to you just now also before, your tuning fork is a certain frequency here. Whatever sound wave you have here that gets reflected back, producing a stationary wave, would also be having the same frequency. In your case, your tuning fork did not change. You're always using the same frequency, so your stationary sound wave that is formed would always be having that same frequency. And also because your frequency did not change, the wavelength is always the same. Okay, so this one, between these two, this one has no change. Only the length was changed. Okay, so if I tell you that this one is lambda over 4 equals to 0.14, this lambda here, sorry, this one is lambda over 4. Wait, let me just erase this. If I tell you this one here being lambda over 4 equals to 0.14, lambda now is 4 times 0.14. Wait, the first two station waves occur when the air column lengths are 0.14 and 0.42. 4 times 0.14, this one will give me 0.56 meter. Okay, from here I can see that my wavelength is 0.56. When it comes to the second one, the wavelength ought to be 0.56 also. Okay, this one by right, the lambda will also be 0.56 meter. Wavelength will be the same for both, frequency will be the same for both. Now for this one, I can still do from the first diagram itself, I can really find out what's the wavelength. I can also do it from the second diagram. I'll show you that you can get back the same answer. So this one I know is going to be how many quarter wavelengths? This one is quarter wavelength, and also quarter wavelength, right? So 3/4 wavelengths is equivalent to 0.42. So wavelength is 0.42 times 4 divided by 3. 0.42 times 4 divided by 3. You're gonna get 0.56 meter. Okay, so no issues. You're seeing now that both are giving you the same answer. So answer is D. Okay. Now there's also another way to do this also. Let me just show you one last step before I end this. Okay, now notice that I kind of drew this to scale here. Okay, right? So you see this one was node. This one was node. At the next formation of my stationary wave, I'm just going to get a node at the other end here, right? If you look at the distance from, maybe I highlight it for you. If you look at the distance from here to here, this one is actually from node to node. It's adjacent antinode. So lambda over 2. Okay. So lambda over 2 here, if I want to find this distance here, it will be 0.42 minus 0.14. 0.42 minus 0.14 meter, because I will take the difference between these two lengths. I will get this length, right? Okay. So 0.42 minus 0.14 equals to lambda over 2. So if you try to do the question again, eventually you will get the same answer, 0.56 meter. Okay, so you can also do it like this. There are many ways to do this. There are three different methods, three different ways to do the same question.